Welcome. In this video, I will review a research paper on computer vision. I should not say that I will review the paper. I will just discuss the paper. That probably is a better word than review. So discuss the paper. It's on computer vision. It's based on neural network, and it predicts the human motion. So neural network based predicts human motion. Okay, so I did not read the paper very clearly or everything. So still I'm just giving it a try based on not how much I have read, so how much I can explain. So yeah. Okay, so the paper title is Dynamic Multiscale Graph Neural Networks for Three-Dimensional Skeleton-Based Human Motion Prediction. So this is the authors. Anyway, so okay, what this paper has done, as I told, it predicted human motion. What does it mean? Let's say you are walking or you are running. So it will predict what can be your next motion. It means that what will be your next hand movement or leg movement or body movement. And in short-term prediction, also long-term prediction. Short-term prediction, immediately after this, what will happen? And long-term prediction, probably after, let's say, after a minute, where you will go or what will be your motion, that kind of thing. So short-term prediction, it is kind of easier than the long-term prediction because things might change. You might change your mind or something else can come up. So yeah, I think this paper for sure performed better in short-term prediction than in the long-term prediction. So yeah, it can predict, but can it predict in real time? I mean, can it just deploy in hardware? Let's say in self-driving car, the algorithm is deployed on the self-driving car. Can it predict the next motion of the pedestrians or next motion of the cars? It's about human motion prediction. So I should not talk about car here for sure. So can it? Okay, so far I saw they did not talk about it, and most probably they did not apply it there or did not go to there. However, they have experimented it with a data set that's CMU, probably Carnegie Mellon University or Human 36 data set. I might give some more information on that. And I think those data sets, I think what they do, they store some images for the sequence of motions and corresponding images. So what this paper did, I think it divided that image set into training and testing, validation probably. I have to see the details. So from the training, it learned how the sequences happens in walking or running case, and then it tried to predict, okay, what can be the next prediction. Probably if you give an input, depending on the learning, it will predict what can be the next motion for this particular object, particular person. So yeah, I think they learned from the training and then they applied on the testing, the separated testing data set, and they found a better accuracy. Whether it is applied on real life or real applications, I doubt it is. I think the paper talks about mostly on the data set, and they are saying they have achieved good performance in some of those motion prediction. It's not that you are taking a photo or you are jumping or you are eating. It's not that in all cases they have got a good performance in short-term prediction or in long-term prediction. Yeah, in some cases they are telling they have got good performance, and they're saying that their performance is better than the other work even the state-of-the-art traditional approaches. Traditional approaches mean it's not machine learning based, it's just traditional engineering approach probably. Statistical data analysis and those things. It's not, statistical data analysis is part of machine learning kind of things, but still, let's say, all the machine learning technology, training, validation, it's not, it probably is the statistics based on rules and your understanding of the thing and define some rules and mathematical formulas, model-based things. It probably be those things that's state-of-the-art, model-based. And also some other machine learning-based, those are not particularly the same architecture and steps this paper has used. And those can be other machine learning approaches like random forest, Gaussian processes. I did not see that. I don't think they talked about the maximum likelihood approach, Bayesian approach. I think that you might be able to relate Bayesian prediction kind of things based on the priors and posteriors and all those things. Yeah, Gaussian data set and just trying to understand the behavior of the data set and try to regression and prediction, those kind of things. And like anyway, random forest or decision trees, finding some sort of rules in the data set and then try to predict. It's not impossible to do that. It can be possible. Anyway, I think this paper, I think so far what I saw, they try to say that they have performed better than Gaussian processes, random forest, state-of-the-art process, state-of-the-art processes, and even some neural network based or recurrent neural network based approaches. Yeah, I think I am not trying to limit myself within some time frame. I'm just trying to say whatever I can say. Anyway, I think the same thing I might be repeating at different parts. I'm just trying to see that, okay, without I show you the other slides and I can give an overview so that you know. Anyway, so let's see, if I go back to the title of the paper, Dynamic Multi-Scale Graph Neural Networks for Three-Dimensional Skeleton-Based Human Motion Prediction. I think there are lots of concepts in here, right? Multi-scale. How do we mean by multi-scale? Okay, multi-scale means I think it can be data in time scale, it can be data in space. I think you are using data in multiple scales. However, the way this paper has utilized multi-scale, it's about graph that relates to human body. And human body, how this graph is generated, it relates to the joints and bones and subparts of an organ or the full parts of an organ. That's how they relate this multi-scale thing. So let's say, so they have formed some graph, right? They have formed some graph based on the, I think they're telling skeleton and it's 3-dimension. So skeleton is formed of different bones and bones are connected through the different joints, and those bones and joints can form all those organs. It can be multiple bones, multiple joints that can form the organ. So it looks like you can define the graph, human skeleton graph in different ways. You can define a graph like, let's say, all the joints are connected. That is just one graph, right? You can say that's scale 1, the bare minimum graph. Even all the joints in your fingers, those can be part of the graph, separate node and separate edge, right? So that's one scale, the simplest scale in this paper that is telling it as a scale 1 graph. So just the joints and all the bones are edges, joints are nodes. That's a scale 1 graph. So what is the scale 2 graph? You connect two different zones to two different bones and connect it and just consider it as a node. It's not just one joint, multiple joints into a node. and then another multiple joints, another node, and you connect them, the edges. I think so far, yeah, I have to check the details. It does not look like that all the two joints in the finger is into one node and another two joints on the finger is another node, or finger and palms, and then they connect it, and then they're telling it different edges, or they probably don't go to that fine-tuning level, but you can definitely think that, okay, let's say the arm, the elbow, and the connection on the palms and hand. So you can just say 3 different node in the hand, and then okay, I think let's see, you are defining one graph with multiple joints and connecting multiple graphs. Okay, I think, okay, what is the scale 1? All the joints are nodes, all the edges are the bones and connected. You create the scale 1 graph. What will be the, I think that's one total scale graph. And scale 2 graph, I think there will be multiple graphs. There will be multiple graphs, and each graph there will be multiple joints, right? Now you can think it in a different way. I think there are two options here, right? You can just see, okay, the multiple joints, you can consider it is one graph and another multiple joints in another graph, and the connecting bone is the edge. That is one way of considering it. Another way is the multiple joints in a graph, you can just consider it as a node, and then multiple joints in another graph, you can just consider it as a another graph and then connecting it. Okay. So in this case, this is scale 2. In scale 2, let's say one organ can have these multiple graphs. And each of those multiple graphs, there can have multiple joints. And on the scale 3 graph, the total hand, that will be one big graph with different joints. Okay, I don't think they subdivided into the scale 2 subgraphs. It's not like this. I think from the picture, as I remember, in the scale 3 graph, all the individual joints, they just put as a dots or kind of different nodes inside that big graph. So I think I have to see how they actually have defined it. I think if we just try to see, and they might not have discussed this in details, it might have just, you can just see, okay, scale 1 graph, just the joints and bones, the total one graph. Scale 2 graph, you will see that multiple, just a multiple thing, 2 or 3, it probably just two parts in an organ and the connecting bone. Leg lower part, leg upper part. These are two different graphs and connecting. The same with hands, two different parts. But in scale 3, you will see the entire hand in one big block and all the joints inside. So you can consider it one. Anyway, you got the picture. So it looks like I have to see how actually they are trying to relate this subgraph or those things. So yeah, I have to check it as I told before. This is just I'm trying to see how much I can explain based on my reading. I did not read it completely. And you have to take a break, water break. Okay, graph neural network, GNN. I think it's a neural network that processes graph. That's why it's called graph neural network. So you are forming the graphs of human skeletal and organs, and you are processing it through a neural network. So as it is processing neural network graphs, it's a graph neural network. And what does graph neural network do? What does graph neural network do? Okay, so you represent your problem in graphs and you feed it to the neural network. What it will do? It will find out the dependencies, the relations of those graphs and different nodes, edges, how they are dependent on each other, how they relate to each other. And for sure, there will be some output representations in some sort of vectors, encoded or not, or whatever. I think there will be some output. And in general, yeah, if I say that there will be some vector output, it is true for sure. But it is the only form of output? Maybe, so far as it looks, what else can it be? Single value, single variable. Usually that's not how things are supposed to work. Still that might come as a factor. Anyway, so three-dimensional is three-dimensional. Human motion prediction, yeah, motion. Yeah, I think walking, what will be the next motion? Running, what will be the next motion? Eating, what will be the next motion? And we're applying this algorithm. No, I really should not say it algorithm. It's just an architecture and corresponding approaches to find out the next motion. Anyway, and why they have used the term dynamic multiscale. Okay, I'm not sure. And did they even explain it? So are they referring it to that the graphic scales are changing dynamically, or is it possible, or probably the interaction within the cross graph? I think scale 1 graph, scale 2 graph, scale 3 is dynamic, whether it's changing over time or the relations are changing over time. In general, they're supposed to change, right, when you're moving. So yeah, I did not see what exactly this term dynamic they are trying to refer it to. So if it is dynamic multiscale graph neural network, okay, it might be that the graph neural network that's saying it to be dynamic. Anyway, let's go through the slides. So this talk is supposed to be organized as accomplishment, overview of the work, methodology used, results on simulation, weakness of the work, future direction, conclusion. So yeah, I think something else could come, like how they formulated the problem, or the different approaches or experiments they have used, and why they designed those experiments and what else they tried. Yeah, problem formulations, mathematical problem formulations, all those things could come if it were a 1 hour long discussion. Anyway, I think I will see what I've written down in the slide, and I'll go from there. And as I told, I might create other videos just depending on this, basing on this paper to bring out the related concepts. So let's go to the next one. Yeah, accomplishment overview, methodology, all these steps. Methodology, I think I can bring the methodology and experiment here. Results and simulation, weakness of the work, future direction, conclusion. Anyway, let's see. So primary contribution. Okay, so far I saw they did not make any any theoretical contribution. I think conceptual contribution, theoretical contribution, I did not say that they have made it in algorithm wise or conceptually how to predict the next motion mathematically or conceptually or algorithm wise. They did not go on that level. What they did, their contribution is the architecture. How they define the architecture, what are the units they use, how they implemented those architecture, and how they utilize the multi-scale graph and their interaction, how they fed into it, and how they process those informations. Those are the contributions. I think they did it differently. Definitely based on some regions. Yeah, but in terms of fundamentally conceptually, I don't think they have done a huge amount of things there. Anyway, when they are defining the architectures and all those neural network blocks internally, there are some math applications. So yeah, internally how those maths are being applied and how those maths are being applied in combination with each other. Yeah, you can see some sort of algorithm approaches or contributions or different things are going on there for sure, but it's not how they try to focus on it. They try to explain it. Yeah, if you try to bring out those explainable AI and can form those mathematical operations and bring out those mathematical concepts out of those and define those things, and if you can apply those just on data, you might get something, some contribution there, but that's not what they try to discuss, right? It is just the way they form the architectures and interactions with the graphs, how they feed, how those multi-scale graphs worked out together to find out the better performance. It's the what is the focus. So what is the primary contribution? Overall, derived and proposed a graph convolutional block, and gated recurrent unit-based architecture and framework. That's their, yeah, they derived the architecture and they propose this architecture for motion prediction, and they're telling that their performance is good. So yeah, they have utilized multi-scale human body graph. They have utilized and proposed multi-scale human body graph. Yeah, you already know, I have already told. And yeah, as I'm telling, they're utilized and proposed. They're proposed because they also are saying that nobody in other work has utilized the way they use this multi-scale graph and how this cross-graph interaction is important and how this cross-graph interaction conveys information about the next motion prediction. Let's say, yeah, they are right for sure, because when you're walking, it's not just your hand movement that defines your word, it also defines your leg movement, leg motion, or your body motion. So how these forces, joints, how these forces are being acted upon across different organs, across different different graphs, that defines what can be your next motion. Okay, so yeah, and another thing is the environment. I don't believe they have utilized this. What is the environment? What are the objects are there in the environment? Those might also take contribution. I think you might be able to define some sort of graph there on the environment graph, environment object or environmental forces like air pressure or sound or obstacles. If you can define some sort of graphs dynamically depending on the environment, and if you can bring those things into this architecture, Yeah, I think in general it might not make sense, but depending on the applications, there might be some use of it. It's not that completely vague. Okay, I have to see if there is any work on it or really it makes any sense or not. Anyway, uh, I think that can be something. So yeah, I can see that input encoding site, MGCU, all those things anyway. So they're using encoder decoder framework. Encoder decoder framework, I don't think it's very uncommon. It can be very common. And conceptually what will happen on the encoder side. Yeah, depending on all those input and data and processing, they'll try to take all those data and try to uh, encode it into some sort of vector representations. Yeah, vector that is multiple information embedded into it. Yeah, if you are studied computer hardware engineering, there will be some sort of encoder decoder. There are some chips that are labeled as encoder encodes. It combines big information into smaller things. Yeah, you will see many different inputs, just many different input pins and just couple of output pins. So it's encoding big amount of information into a small amount of information, right? That's what you have to know. So yeah, that's what is going on. All the inputs and graphs, multi-scale graph, cross interaction, all those things, and they're encoding into some information. And yeah, this is passing through some neural network, and they are telling it that MGCU, multi-scale graph computational unit, multi-scale graph computational unit, it's just a bigger block, and inside it there are some more neural networks, small. I think the building block of MGCU are graph convolutional block and cross-scale fusion block. So those are inside MGCU. So yeah, this is a neural network. All these are individual neural network. This is neural network. This is neural network. Anyway, these are on the encoding side. Okay, I was on the encoding side. Anyway, so yeah, the encoding, why it is, as I told, encoder decoder format. Encoder, they are taking all those information, yeah, from single scale or multi-scale, cross-scale graph and all those things, and encoding into some sort of representation, encoding all those information. On the decoder side, taking this encoded data and just predicting the next move. I think decoder, based on this encoded information, and as they are coming in sequence, the decoder is predicting the next motion or next move. So yeah, and on the encoding side, I think they are using a bigger neural network block, and inside there are multiple different neural network concept they use, and they are used in a different way. Anyway, so let's say graph convolutional block. It works on the single scale. I believe SS means single scale. Yeah, that makes sense. Single scale graph convolutional block. They're finding the features. And then this cross-scale fusion block. I think it is combining fusioning information from multiple scale graphs. Let's say scale 2 graph and scale 1 graph. This is cross-scale. Information from cross-scale 1 graph is they're combining fusion. Fusion means just data from different things and fusioning into one thing, right? Just data merging and creating some new meaning and new meaningful data. Same way, scale 2 graph and scale 3 graph interactions, and then fusing them into new information. And all those things are being encoded into a factor kind of things. Okay, on the decoder side, they are using graph-based GRU, then gated GRU. Okay, GRU. is it graph? I think it's also graph recurrent unit kind of thing. GRU, yeah, and G means gated. Okay, let me see. I can just Google it a little bit. Anyway, just got confused. Okay, yeah, I believe I also told the same. Gated recurrent unit. If not, I have to say. And G, I'm not sure, I just got confused. This G is for gated and this G is for gated. So why is it double gated? It looks like G is for graph and the G is for gated. Anyway, so yeah, on the decoder side, this is what it is. Gated recurrent unit. I think it's a recurrent neural network, but it's gated, right? The recurrent neural network, you know that the issue with the recurrent neural network that it cannot process long sequence of data. It can process short sequence of data. So yeah, short sequence of data recurrent neural network. I think short-term motion prediction, the regular recurrent neural network can be used, depends how short. And it cannot memorize much information from the past. And you have the issue of gradient descent, vanishing gradient descent in the uh, recurrent, recurrent neural network. Gated recurrent unit, I think it has the update gate and the forget gate. That's how it can remember things longer, and it can also identify which information to forget and which information to keep in mind. It will forget the unnecessary information, and it will find the most important information, and it will remember this. So that's how the gated GRU, and this is graph processing. Anyway, I think LSTM, that can be one another approach rather than GRU, long short-term memory. So yeah, that can also remember much. And instead of GRU, LSTM could also be an option. LSTM usually gives more accuracy, and in general, LSTM takes more computation and probably more memory kind of things in general. Okay, I might have to verify it, but to the best of my knowledge, that's what it is. Yeah, in that case, LSTM can be an option. Even bidirectional LSTM can also be an option if you want more accuracy. Let's see how to apply it can be tricky, and I'm not sure if anyone has done it. Bidirectional LSTM. Yeah, the sequences are coming, and after some sequence, you're also trying to feed from the other side. Let's say, if you want to use bidirectional LSTM, you might want to feed different scales graphs from different side and try to relate to back kind of things, or forward and backward together, and try to see if you can get a better estimate of the next prediction, next motion prediction. Just if the prediction doesn't match, if the prediction match the forward side, you might also, or suddenly it changes, it doesn't make sense, you can also try to see it from the other side of things and try to see if anything can be done. Anyway, it just, I did not put much thoughts into it, just saying it. So anyway, I'm talking too much, as I told. I will say whatever comes to my mind. Anyway, graph convolutional block, it's actually a convolutional neural network. Convolutional neural network, that's the CNN. Yeah, kind of CNN, just filtering and edge kind of things, those kind of things. Yeah. So single scale, graph convolutional, anyway. So yeah, Okay, I think I have said enough for this slide. Why is the research important? Okay, so yeah, I think to become a research to be important, it has to achieve something. They achieved better performance than many of the state-of-the-art traditional model-based or other neural network-based algorithms in terms of predicting the next motion or next move. So they have achieved something there with better accuracy and some of the benchmark dataset or standard dataset. So their achievement can be seen to be good. However, in terms of conceptually, mathematically, rule-based on the understanding level, they did not derive much on this. It might be more on the architecture side. And the mathematics inside this architecture, that's the hidden thing. There must be going on something there. So yeah, and nobody else tried it. That can be one other thing. Nobody else tried these things, or nobody else tried this approach and found this type of things. So yeah, that's another contribution that we can see, and they're telling that they can predict the long-term motion prediction. They're good on that, and short-term motion prediction. They're telling they also achieved a good result there. And also they're telling that they tried multiple scale graph and cross scale graph interactions. Nobody else did it this way. Though they have utilized scale 1 to 3 graph, however, they tried scale 4, scale 5, and they thought they found that the scale 3 graph is the best that gave them the better result. Yeah, it might make sense that scale 3, yeah. However, there might be the case whether scale 1, 2, 3 or 3 are required. Can it be simplified, or can it even be done one step more? I did not see they have done it much more. I think depending on the context, sometimes discarding one of the scale and sometimes bringing one another bigger scale. Probably start with some bigger scale first and then go to the lower scale, or probably if the LSTM and bidirectional things, if there is anything there. Yeah, they did not, what I'm saying might not even make sense, but still they did not do any work on that thing. But what they have done is they tried scale 4 graph, scale 5 graph, and they tried to implement it. And they found out, okay, scale 3 graph is the best thing, 1, 2, 3. They found it. Anyway, in terms of contribution, yeah, let's see what I've written down. The work outperformed for certain motions. It's not that all the motions. Motion, I mean jumping, walking, running, eating, shooting, punching. The work outperformed most of the rest of the artwork. Some neural network based work for motion predictions. Even some neural network based work for motion prediction, they outperformed. No other work considered enough relations from multiple scales. Okay, and they also argue that relations in various scale graphs carry important information about human motion. Yeah, logically for sure, it does. So some related work, yeah, as mentioned in the research paper itself, not that I have read them. Hidden Markov model, Gaussian process, random forests. I might have mentioned them lightly. I have to read the individual papers, how they have used all those things. I might have seen videos, how Gaussian process is used for movement predictions in corridors, viewed from the video images. Random forests, yeah, it can be just a rule-based if you use the, yeah, I did not say exactly the paper they are referring what they have done it. Okay, some deep network-based, recurrent neural network-based. They use recurrent, in this work they use recurrent neural network, but not the plain vanilla recurrent neural network. So some other feed-forward networks. I think recurrent neural network, they process the sequence And feed-forward networks, they are not for sequence processing. Anyway, these are some of the works. And if you go to the target tracking, target trajectory, yeah, you will see some other work. I think the traditional approach has different sorts of Kalman filter kind of things. So the trajectory, but can it be used in human motion prediction? That's a tricky question. In that case, you have to apply Kalman filter for each of the individual components of the graphs. I think in that case, you probably have to not scale 4 or 5, or it might have to start with scale 3, 4, 5. You have to see scale 4 or 5. Scale 4 or 5, let's see. I might have skimmed it, but not exactly sure how they have defined it. It can be, let's see, on the lower side of the body, right side of the body, scale 4, lower bottom of the body, upper bottom of the body, scale 5, that is scale 4, probably 3 different parts. The shoulder and up, the main body part, and the lower body part. Yeah, if you want to define scale 4 or scale 5, I think this particular paper that I'm reviewing or discussing about, they have used a similar thing, the bigger level things. Okay, let's see. So I'm going into the Kalman filter, whether you can use Kalman filter for this motion prediction. It's not impossible, for sure. In that case, you have to apply the Kalman filter on the bigger scale. Scale 3, 4, 5. Scale 2, the prediction trajectory of the individual scale 2 graphs. That can be too fine-tuned, fine-grained, probably. Yeah, even if you try to go through the scale 3, it's about motion prediction, right? In that case, yeah, I think scale 2 graph still has a value. If you try to use Kalman filter to predict the trajectory, yeah, scale 2 graph, you can see each of the scale 2 graph, the big graphs, you can try to predict their next motion, next place, and try to predict the next motion. Yeah, it's not impossible to do the model-based thing. And what else can be there? Anyway. Okay, so come to the methodology section. This is the MGCU. The entire block is the MGCU. This is the single scale graph convolutional block. It is working like the regular convolutional neural network, finding the edges, understanding the features, individual features of those dataset images. And scale 2, yeah, it is also working on the scale 2 and scale 3, trying to understand the individual features of those images, trying to understand the features or boundaries, or depending on how this is used, the important part of those things. It's not about always boundary or edges. Sometimes it's about the, yeah, I think how use those filters. Anyway, that's a different thing. So, cross-scale feature collection and fusion. So this is the feature collection, understanding the features. This is the cross-scale fusion. It is fusioning data, I can see. So whatever is coming from there is an input. Whatever is coming from scale 2, input, and it is for this one, scale 2 and scale 3. And it is again whatever is output. Next, this one is coming here. Anyway, so you can see how this data is being processed on the encoder side. So this is the overall architecture. Okay, one another thing, let's say, so this is just one layer. They have used 4 different of such layer on the encoder side. Okay, so far I remember from the paper, yeah, 4 different such layers they have used on the encoder side. And you see the difference. I think from the data, they also use the difference operator. Difference operator, I think difference means, let's see, I think some sort of vector, they are finding the difference in the sequence of images in terms of, I think, position, velocity, and acceleration. Yeah, position, velocity, and acceleration. So yeah, those are also being used in the input side and feature learning, those kind of things. And so far I remember, I think when they have used multiple order difference, the approach was better. Multiple order means, let's say, if you are using only position difference, that is scale 1. If you are using both position and velocity difference features, then is scale 2. If you are using position, velocity, acceleration, all 3 difference from the input data and processing it on the neural network, then it's scale, sorry, it's order 3. I believe I used 1, 2, 3 order. I believe in the paper they have used 0, 1, and 2 order. And 0 to beta, I think the symbol is the beta. Anyway, take a look in the paper and you'll know. Okay. And on the decoder side, yeah, gated GRU. And they are giving the next motion as an output. Results and simulation. Yeah, I just given some partial result here. I did not copy the entire, all of the information on the paper. So the data sets they used, human 3.6 million data set, CMU motion capture. Yeah, those are motion, short-term motion prediction. Okay, this is the performance of the short-term motion prediction. Okay, let's see. Those images, they will also have motion information. Yeah, those data sets, motion information. And I think there is all the joints and all those things information will be there so that they can build up those graphs, and then otherwise this result would not be possible if the joint information would not be there in those images. Or probably something should be there so that they can construct those graphs. But so far I remember the joint information is there in these data sets. Short-term prediction, I think they might have preferred prediction in the next 400 millisecond. That is the short-term prediction, and anything over 500 millisecond, what will happen after 500 millisecond, that's the long-term prediction. Yeah, you have to verify it with the paper, but to the best of my knowledge, yeah. So let's see. So 8163, okay. Yeah, this is the how short-term prediction they are using. These are all the different other algorithms approaches they have compared this work with. And in terms of error or performance, what is they used? They used the mean average error. Mean average error, it's just the difference. It's just one norm difference. It's not the Euclidean error. It's not the second norm. It's not the root mean square error. It's not that. It's just the mean average error. Mean average error, I think what it can do, it can keep the error as it is. It's not amplifying the errors, or it's not amplifying the good result or bad result. It's not amplifying the it's not I think the reverse amplifying the errors or success, those kind of things. So mean average error, they're keeping the error as it is. So on this side, here you can see the mean average error, the performance, right? Okay, this is the time, and this is all the different mean average error for all those algorithms and for different level of short-term prediction, short-term motion prediction. Now you can see usually these are smaller, that means their error is less than them. Okay, as I'm talking about mean average error, they are using mean average error as the loss function when they are training on the data set, on the training. I think in machine learning, when you train, there is some loss function. Sometimes you might be using it objective function, scoring function. In machine learning literature, I might have seen loss function more than the objective function or scoring function. Those might be more on the engineering optimization side. That's what I might have seen it more. And in general, I'm not the big expert, so I might have not seen so many things like the big experts and big geniuses. No, anyway, with the limited thing. So yeah, let's see if I can refer to the loss function here. So mean average error, there's the loss function they have used. And usually if it comes to loss function, it's the prediction and actual, the difference, and some sort of calculation on it. That's the loss function. Anyway, so yeah, they try to optimize that when they are training their architecture, their approach on the training data set. They are training it so that they get a lower prediction error, the lower losses, and they will for sure will try not to overfit and not to too much underfit, too much overfit. They'll try to keep a balance so that it performs well in the test data. And the result they are saying, I believe these are on the test data set. That's what it is supposed to be, irrespective I believe or not. That's what it is supposed to be. But if it is other way, I may try to clarify in another video. Otherwise, you can verify yourself. So anyway. So long-term motion prediction. Okay, I still see up to 400 millisecond. Here is still 400 millisecond. Either I have copied the wrong table, or I might have to check the information. It might be just 300 millisecond kind of things. Let me see, I can probably verify it. Okay, short term, anything less than 500, long term, anything more than 500. So it might be the case that I might have copied the wrong thing. Anyway, let me see, I can open the paper, results paper, and show the result. Okay, if you can see the screen, I believe sharing should work because I'm using the Acrobat Reader as the sharing. So this is, okay, we see 1000 millisecond. Still, this is less than the others and all the different actions. Okay, what can be the weakness of the work? Yeah, I might have told it before. It probably is harder to come up with the weakness because it's mostly on the architecture side. So unless you try to see how different architecture works, I think for weakness, it can be tried to see all the different concepts they have used in terms of architecture or the different types of neural network they have tried to use. Is there any limitations for the type of task they are trying to perform? Those are the places to look for if there is any weakness, or can you make it better, or if the choice they have made, is it the best choice or not? If not, then that can be a weakness. And also how the different components of the architecture is interacting with R and all the information they are processing, is there any limitations? One thing is you can change those and see whether whether you can improve the performance or not. That's one thing, but that's not the kind of weakness you can say. I think in terms of weakness, I think you have to logically think, okay, as I understand, right? You have to logically think, okay, so they're using this approach or that approach, whether this is the right fit for this kind of work. If that's not logically right, or something else is supposed to work better, or some other configuration, logically, conceptually, then you can say, okay, this apparently looks like to be a weakness. Then you can try a different architecture, different approach there, sigmoid, Adam, or all those things. I'm just giving some example, not very related to these ones. I have to see what exactly they use there, or connecting those, scaling those things conceptually. Is there any weakness? Yeah, you can connect a different way and show that your performance is better. But if you can think logically, I personally will think that probably is something to put more value on in terms of weakness. Logically, if you can see, okay, this is logically is a drawback. Logically, conceptually, mathematically, the way the architecture is working or the way the things work, it doesn't make sense, or it's a weak way of doing things. That's the weakness. But in terms of improving, arbitrarily, trial and error, from the intuition, try different things and see what happens. Yeah, you can get a better result. That might give better result in most cases. That can be good work for sure. And you can use some explainable AI concept. I'm not sure how much I can relate to this. And if you can explain that the better result, still that probably can be say good work. Anyway, so okay, the information that I put, so the work did not perform well in those cases. Smoking detection. Anyway, I have to verify this if I wrote it right. But if it did not work well in these cases, that's the weakness of the work. But I cannot say that this is the weakness of the approach. Yeah, indirectly, yes, it is. But it's not the weakness of the concept itself. Anyway, is GRU the most suitable choice? That's probably something you can see. Can LSTM be more accurate? Can LSTM perform better in longer sequence than the GRU? Can bidirectional LSTM GRU provide better performance? For cases where the result did not perform well, can you improve it to achieve less computation? Can we use scale selectively? I might have told it in the beginning or randomly. Not all of the scales all the time. Some of the scales some of the time, other scales in other time. Future extension of the work. Yeah, just see if anything can be done here. Application specific adjustment, more order differences. What else can you apply here? In integration with surrounding object detection. Yeah, as I might have told, one more graph of the environment, objects, their relations, interactions. It might relate to the application. It might not be a very general case. And can you integrate Kalman filter into it? Anyway, I probably is thinking very loudly here. Okay, that's all. So yeah, verify with the paper, verify with the other information. And as I told, I did not read the paper to the extent that I understand everything again and again. So feel free to doubt whatever I have seen, I have told. And yeah, listen to the expert, genuine experts. Okay, bye for now. I believe I'll come back. Probably with more questions and answers, with more information on the whatever I skip, mathematical part, problem formulation part, or probably the related more on the related neural network information. Anyway, thank you. Bye-bye. Have fun.